Day 53, Honors Physics, Rotational Equilibrium Torque, Problem 29. Here's an interesting problem. It's a balanced mobile, kind of like the thing that hangs above like a child's crib. I'm starting at the bottom here, so I started down here, and then the final part of the problem is up in the upper right, but this is what I start with. I'm starting with the lower rod, and I drew the rod as a horizontal red line. But you got to figure out the weight of that rod because it's not negligible. It says the rod is 6 newtons per meter. That's in the givens. And I know that rod is 45 centimeters long, 0.45 meters, because 15 plus 30, it's 45 centimeters, 0.45 meters. Therefore, the rod itself weighs 2.7 newtons. And I'm putting that weight at its center of gravity. Half of 45 centimeters is 22 centimeters, 22.5 centimeters. So this is the weight of the rod at its center of gravity, which then is 7.5 centimeters from this string holding up that bottom rod, because this is 15 centimeters, obviously not to scale, because this length right here is 22.5 centimeters, half of the total length of the rod. Okay, I know this weight over here is 3 newtons, that's given. I have the weight of the rod down, and then the unknown weight that I'm looking for, the clover at the other end. So I'm picking point A as my point of reference to calculate torque, because that will get rid of the force T1, the tension in that rope. And what I'll have is over here now, torque with reference to point A on that lower rod, clockwise torque equals counterclockwise torque. Well, the clockwise torque with reference to point A will be this force pulling down, trying to make it rotate clockwise, times its distance of 7.5 centimeters. So 2.7 newtons times its distance, 7.5 centimeters, doing everything in centimeters, plus this weight, which is the force over here, times its total distance from point A. The total distance from point A is 30 centimeters. So that's the distance. Always measuring everything from your point of reference. Equals the counterclockwise generating torque. This 3 newtons is trying to make the whole thing rotate counterclockwise. It's that force, 3 newtons times its distance in centimeters, 15. The only unknown is W sub 1. You calculate W sub 1, you get an answer. Once you have W sub 1, there are 3 forces that are down. Those 3 forces down have to be then balanced translationally by T1. So T1 is the sum of those 3. So you'll figure out W sub 1 and plug it in over here as a known to get the tension in T1, because you use that for part 2. Basically, part 2 of the problem is just repeating part 1. Now you go to the upper bar, which I'm doing up here. It's the same problem with different numbers. A little bit easier, though, actually, because the upper bar is a half a meter long, so it's 3 newtons in weight, because 6 newtons per meter times a half a meter gives you a weight of 3 newtons for that upper bar. In the dead center point, center of gravity of that bar, it's 50 centimeters long total. 30 plus 20 is 50. So that point is 25 centimeters from either end. 25 centimeters here, and then 25 centimeters here. And since this is labeled as 20 centimeters, this must be 5 centimeters. Just like, and I didn't do it for you, but you'll be able to do it. From point B now, calculate the torque. It'll be basically the same thing you have at the bottom of the page here, except for different numbers. 3 newtons times this distance, clockwise, plus W sub 2 times the distance 30 centimeters will equal T1, which you know, that's from part 1, that's a known number from part 1, as we did at the bottom of the page here, times this distance. So the only unknown will be W sub 2. They could also ask you later on for how much tension is in upper rope. I didn't ask you for that, but T2 would be the sum of those 3 numbers right there. That would be an extra question you could be asked.